Hello, hello, hello. This is Nicholas, and paradoxically, I'm going to start off this explanation video with a paradox. Right? I'm going to make you more confused when I just started. No, that's not my goal. Anyways, so the paradox, maybe you're familiar with them, maybe you're not. It's a whole branch, really, but they're known as Zeno's paradoxes, and I think the guy was an ancient Greek. And so he had a real problem with infinity and infinitesimals. And why am I talking about this paradox? I'm talking about it so that to give some motivation for the definition of the derivative. So Zeno said that, imagine we have a bow. This is a bow, not a big D, it's a bow. And, we've got this arrow. This is a bow and an arrow, all right? And we shoot the arrow, and it does, it does a parabolic trajectory from physics, kinematics. And so it does a parabolic trajectory, and then it hits the ground, and that's that. But no, so he thought, well, okay, let's imagine that we take a snapshot, right? I hit the photo, get it? Oops. We take a snapshot in time, okay? And we say to ourselves, well, at that instant in time, the bow isn't moving, right? The bow has no velocity. Why? Because velocity is change in distance per change in time, and there can't be any change in distance if there's no change in time. So in other words, the change in distance is zero and the change in time is zero. So we get 0 over 0. The velocity is undefined. Or indeterminate, not undefined. It's indeterminate. The velocity is indeterminate. So we need to do more, and that's what calculus is going to answer, to actually find this instantaneous velocity. The rabbit hole that Zeno goes down is he says, well, this trajectory here, this arrow that I've drawn, this trajectory is really just an infinite collection of all these snapshots. And he says, well, if each of these snapshots in time has zero velocity, in other words, the bow isn't moving, and if the trajectory is just composed of all those snapshots, how can the bow move at all? Now, I hope by the end of the video you're able to see the flaw in this argument, but this is just something that the derivative can answer for calculus. Okay, now, on to the calculus. So, imagine we have a positive increasing function. Looks like maybe an exponential. Doesn't really matter what it is. We'll call it f of x. Okay, and the whole point of the derivative is to answer the question about instantaneous rate of change. That is, I probably should even write it down because I think it's important to address it. See, I'm already spelling bad. Instantaneous. There we go. Rate. I know how to spell rate, and I know how to spell of, and I know how to spell change. And look at this. I mean, it's an oxymoron, right? Instantaneous rate of change. There can't be any change in an instant. Well, we are defining we're going to define the derivative through the limit. And the limit, like I said, is not concerned with the moment in time, in other words, the instant in time in the arrow's trajectory where there is no change in time, but we let the change in time go to 0. In other words, what we're going to do is, let's say we have a point x here, and let's say this is x minus some distance h and x plus some that same distance h. And so at this point here, this y value, that's obviously f of x. This is f of x minus h. And that's f of x plus h. Now, if we were to find the if we were to estimate first, let's estimate. If we were to estimate the change from f of x minus h to f of x plus h, well, the average rate of change would be a secant line going through those 2 points. So in other words, it would intersect just those 2 points, just here and just here. That's what a secant line is. Secant line intersects only 2 points. Or a secant line intersects 2 points, a tangent line intersects only 1. So for example, if we have a circle, that's a secant line. This right here is a tangent line. It only touches at that point right there. Okay, just so you know what I'm talking about. Okay, now we can say that this here is the secant line. The slope of that secant line is the I'll write it as m sub secant it's the average rate of change from the starting point, this f of x minus h, to our ending point, f of x plus h. Okay, now imagine with me that we were to let h get smaller and smaller and smaller. And for now, let's just get rid of f of x minus h. We don't really need that. Let's just consider, we don't even really need this too. Let's just consider the tangent line, or secant line, the secant line, getting ahead of myself, intersecting at these 2 red points here. Okay, now what we can do is we can let h get let it get smaller and smaller. And so what that does is that pushes the point x plus h closer and closer to x. And likewise, it pushes the point f of x, the y value f of x plus h, closer to f of x. Now, let me redraw the graph so that, imagine if it's zoomed in. If we were to zoom in on this graph at just right around here, where we get close, if we were to imagine zooming in, then notice if this is f of x and this is f of x plus h, maybe let me draw the curve to be a little bit more dramatic. Okay. This is f of x, and this is f of x plus h. Now, the secant line going through those points, see, it doesn't even look like a secant line, and it's hard to draw because it looks like it's touching the curve at more than 2 points, but really this is a secant line. It only touches the curve at 2 points, I promise. Now, the idea is that, again, if we were to zoom this in even more and let this get really, really close to f of x, then what would happen? Oh, wow, what would happen? What would happen is that the secant line would turn into a tangent line. The secant line would approach a tangent line. Why? Because as these 2 points get closer and closer together, they become closer and closer to coinciding. In other words, you would have this f of x, and then you'd maybe have f of x plus h right here. And it would be getting super close to intersecting just at f of x, but there's technically 2 points. So as you let h go to 0, the slope of the secant line approaches the slope of the tangent line. And so what we define this to be in calculus is the instantaneous rate of change of the function f at x. So the slope of a line tangent to the curve of the graph f of x at the value x is what we define to be the instantaneous rate of change of f at x. As an example, if I consider a parabola going like that, then it should make sense that if I were to draw a tangent line at x equals 0, right, it would be coincident with the x-axis. In other words, they would overlap. And so the slope of the tangent line of the on the graph of x squared at x equals 0 is 0. And so we say that the instantaneous rate of change of x squared at 0 is 0, because the slope of the tangent line at 0 is 0. Okay, now what I have said in math speak is that I'm considering the limit as h goes to 0, our distance h, of f of x plus h minus f of x over, so I'm really just doing slope formula here. I'm really just doing y2 minus y1 over x2 minus x1, because, these shouldn't be exponents, these should be subscripts. Y sub 2 minus y sub 1, x sub 2 minus x sub 1. Because really, that's going to be the slope of the secant line, right? That's the slope of any line, y2 minus y1 over x2 minus x1. And so I'm letting the secant line approach a tangent line, so I'm letting h go to 0. So this is our y2, this is our y1, and now we do minus x2, which is our x plus h, minus our x. And we can write this a little nicer as limit as h goes to 0 of f of x plus h minus f of x over h. The x's cancel out. And this right here is the derivative of f. It's the derivative of the function f, and we write it as, well, there's a number of ways, I'll get into that, but that is the limit definition of the derivative. That is how we define the derivative in calculus. And we write it with a little prime. Oh, that was Leibniz who came up with that notation. And he actually came up with calculus first. Newton gets all the credit, but Leibniz did it years before. I won't get started on that now. But so that's the limit definition of the derivative, what I circled. It's also written like this by Leibniz, but it's also written as d over dx of the function f of x. This is Newton who wrote this notation. And this might be a little different than what you've seen before, because you might, I hope not, but you might be tempted to just say, well, I can just cancel out the d's and then just get 1 over x. No, you cannot. The d over dx is an operator. It's not the d is not a variable, it's an operator. It stands for the derivative with respect to x. The d here, the derivative with respect to x. That's what the d over dx means. So don't cancel out the d's, just know that it's an operator, and so with an operator, you don't cancel out anything. Now, another way you could write it is the derivative of f of x with respect to x. That's really the main 3 ways you can write it. This is probably the most common, but this is very well known. This you don't use quite as much. Okay, so I think it would be wise to find the derivative of the function. Let's find the derivative. Let's find, using the limit definition of the derivative, let's find, if we have the function f of x being, I don't know, x squared. I picked x squared. We want to find f prime of x, the derivative of f with respect to x. Now, that is the same thing as the limit as h goes to 0 of f of x plus h. So f of x is x squared. So f of x plus h is x plus h squared minus x squared over h. And this is the same thing as x squared plus 2xh plus h squared minus x squared all over h. We're still taking the limit as h goes to 0. And now we can cancel out the x squareds, and we can pull out a factor of h to get the limit as h goes to 0 of h times 2x plus h over h. And now notice, this is what was making the limit indeterminate to begin with, because if we did just plug in h for 0, then we would have gotten 0 over 0. And that's why in the original Zeno's paradox, we got 0 over 0. So we can cancel out those h's, and we now get the limit as h goes to 0 of 2x plus h, which, as h goes to 0, you just get 2x. So the derivative of x squared is 2x. Now, what does it mean? What does it mean? It means, if we were to consider this part poorly drawn parabola to be x squared, then the function 2x tells us the slope of a line tangent to the curve of x squared for any particular value of x. For example, try to draw it a little better. This is x squared. Let's say this is the point 2, and this is the line tangent to the function f at x equals 2. So it just touches that point x equals 2 and nowhere else. And we want to find the slope of a line tangent to that curve. Well, it's by the derivative, it's just 2 times our x value, 2. And so the slope of that line is 4. That's it. I mean, it's really that simple. So the derivative is really an instantaneous rate of change. Maybe a physics note is that if, for example, we define velocity to be the change in x per change in time, like how we did in Zeno's paradox, the way that we write this using calculus is that velocity is the derivative of x with respect to time. Because as delta x and delta t approach 0, that just becomes the limit definition of the derivative. And likewise, and this might be good for me to mention, acceleration is, from physics, change in velocity per change in time. And we could write this as the derivative of velocity with respect to time. But what is the derivative of velocity? Well, it's just the second derivative of position. In other words, the second derivative is the derivative of the derivative. So, for example, if I were to take the second derivative of x squared, then I know the first derivative is just 2x. So now I take the derivative of the derivative. So if I were to take the derivative of the derivative, I would get the limit as h goes to 0 of 2x plus h minus 2x f of x plus, oopsies. I knew I plugged that in wrong. 2 times x plus h minus 2x over h, which is the limit as h goes to 0, 2x plus 2h minus 2x. Those cancel, and we divide by an h. So the h's then cancel, and we get an answer of 2. So the second derivative of x squared with respect to x is 2. So what does that mean? It means that it's a little tricky to interpret, but so basically it tells you that, see, let's picture the graph of 2x now. If we were to picture the graph of 2x, it's going like, oh, wow. It's going like that-ish. So what this tells me is that the rate of change, or the derivative of 2x, is 2. In other words, the slope of a line tangent to the graph of 2x at any particular value of x is always going to be 2. And that should make sense that it's a constant, because the derivative is just the slope of the line tangent to the curve. But since the graph is already a line, the tangent line and the graph of the normal line just coincide. And in general, the derivative of d over dx of cx, where c is just some constant, is just always going to be c for the exact same reason. One other thing I would like to mention is that if I have, let's say I'm taking the derivative of a constant. If I picture the graph of a constant, what does it look like? Well, it looks just like a horizontal line. Y is equal to c, right? Just some constant. What's the rate of change of a horizontal line? Well, it's 0. It's not changing at all. It's keeping the same value of c. So the derivative of any constant is always 0, because it's not changing. A constant never changes. That's why it's called a constant. It's kept the same. Okay, and so a common notation is that, so since acceleration is the derivative of velocity with respect to time, and velocity is the derivative of position with respect to time, we say that acceleration is the second derivative with respect to time. And this is how we can write it. It's a little weird with the exponents, but it's d with the exponent of 2x over dt squared. So dx squared over dt squared, or d squared x over dt squared. That's how you write it. And that should make sense because acceleration is the derivative of velocity, and velocity is the derivative of position, so their acceleration then is the second derivative of position. Maybe as just a funny joke, I know everyone probably knows about position, velocity, and acceleration. Well, what comes after is jerk, the third derivative of position with respect to time. So sometimes you'll see shirts, probably you've never seen this in your life, but it'll say, don't be